Hello everyone. Today I am here to present our paper Beyond Fusion, Modality Hallucination-Based Multispectral Fusion for Pedestrian Detection. Hello everyone. Today I am here to present our paper Beyond Fusion, Modality Hallucination-Based Multispectral Fusion for Pedestrian Detection. First, pedestrian detection is a fundamental task for many downstream applications. And many previous works have been proposed to use two-stream architectures to combine visible and thermal information to improve detection performance. Since thermal images can capture more useful information at night time, compared to visible images. However, these visible thermal fusion-based methods have no ability to obtain useful information from the visible branch under poor visibility conditions. Sometimes, the visible branch could even bring noise into the combined features. In this paper, we present a novel thermal and visible fusion architecture for pedestrian detection. The main idea is the modality hallucination technique. As illustrated in this figure, in the day image pair, pedestrians are easily recognized on both thermal and visible images. In this way, we can learn a good thermal to visible mapping through the hallucination network. In the night image pair, we can still generate useful visible features using the learned mapping. Specifically, instead of simply using two branches to separately extract thermal and visible features, and then combining them, we introduce a hallucination branch to learn the mapping from the thermal to the visible domain, forming a novel three-branch feature extraction module. We then adaptively fuse feature maps from all these three branches. Here is the overall architecture of our proposed multimodal fusion network for pedestrian detection. Except for the visible and thermal branches, a hallucination backbone is added to the traditional two-stream fusion network, and a hierarchical multimodal feature fusion (HMFF) module is further designed to combine features from all three branches at multiple scales. We perform modality hallucination by minimizing the hallucination loss. The goal of hallucination loss is to make the hallucinated feature mimic the visible feature. We adopt the L1 loss as the basic hallucination loss first. Furthermore, we found that visible images captured at night are usually in bad conditions, containing less meaningful color information. In that case, it is meaningless and would even bring noise into the mapping function learning procedure if we still enforce the hallucinated feature to strongly mimic the visible feature. So, to avoid negative feature hallucination, we propose an illumination-aware loss which assigns a lower weight to the hallucination loss of images captured at night. Moreover, to increase the hallucination efficiency, we enforce the hallucination procedure to focus on the pedestrian targets by further introducing a mask weight to the hallucination loss. Overall, the final hallucination loss is defined as a weighted L1 loss, which is formulated as this. In that way, day image pairs would get higher illumination weights than night image pairs. That is, the difference between visible and hallucinated features in good light conditions is penalized more than difference in bad light conditions. And we set the day weight larger than the night weight to encourage the hallucination network to focus on mimicking good visible features. The features from the three branches need to be combined before being fed to the detection head module. Unlike most existing visible thermal pedestrian detection methods which have only features from two branches to be fused, we have three streams of features to deal with. To make the fusion module easily learn the relationship between each modality, we propose a hierarchical multimodal feature fusion (HMFF) module to gradually fuse features from the three branches in a two-step fashion, as illustrated in the figure. Two different fusing strategies are employed according to the relationship between modalities in the two steps. Specifically, we design a modality difference-aware fusion sub-module for the feature integration from the visible and thermal branches in the first step. In the first step, we first get a weighting vector of visible and thermal branches. This weighting vector is obtained from the modality difference map between visible feature and thermal feature. The intuition of this weighting strategy is that the modality weights should be intrinsically related to the difference between the two modalities. That is, when the features from the two modalities are similar to each other, the fusion weights of these two modalities do have not much impact on the detection results. In contrast, when the difference between the two modalities is large, it is crucial to determine which modality is more reliable. After the first fusion step, we can now ensure that the thermal visible combined feature and the hallucinated feature are both informative. Then, we can perform a further fine-grained fusion strategy in the second step. To achieve this, we employ the Shea layer to first channel wisely enhance the two features and then add them to get the final fused feature. This fused feature is then fed to the detection head to get the final detection results. Here gives the examples of our method and the baseline model. The baseline model is created by deleting the hallucination backbone in our model. As can be seen, our method can generate more accurate bounding boxes and correctly detect pedestrians under difficult situations compared to the baseline model. To have an intuitive understanding of the hallucination procedure, we further visualize a set of feature maps to show the change of hallucinated features as the training process deepens. As shown in the figure, the hallucinated feature map looks more like to the thermal feature map at the beginning, see the black dotted line box. However, as the training goes on, the hallucinated feature map becomes more similar to the visible feature map than to the thermal feature map, see the red dotted line box. We also visualize feature maps to demonstrate the effectiveness of the hallucinated features. As in it is difficult to recognize two pedestrians in the visible image, owing to the low illumination condition. The corresponding visible feature map also contains no meaningful activation, while the thermal and hallucinated feature maps look more meaningful. Moreover, in the first row, the fused feature map with hallucination is much better than without hallucination in the second row. Thanks for your listening.